Before we talk about soap, before bacteria, before viruses, I want to tell you a story. Are you ready? I want to tell you about a man who tried to make sense out of chaos. The year was 1869. A Russian chemist named Dmitri Mendeleev stood before a room of scientists in St. Petersburg. He had just presented something audacious, a table, a pattern, an arrangement of all known elements organized by weight and behavior. But there were gaps, empty squares. The other scientists stared at him.
"Where are the elements?" they asked.
"They haven't been discovered yet," Mendeleev said. The room erupted into laughter and scorn. "You're guessing. You have no proof. This is speculation, not science." One scientist called it a house of cards. But Mendeleev didn't come from nowhere. Mendeleev was the youngest of 17 children, born in a frozen corner of Siberia. His father went blind when Dmitri was young. His mother, Maria, took over a glass factory to keep the family alive. When that factory burned to the ground, she made a decision. She would take her youngest son, the one who showed promise, and get him an education, no matter what it took. So Maria Mendeleev took her teenage son and traveled 3,200 kilometers across Siberia. That's like traveling from Accra to the Mediterranean Sea. She did it on horseback, by carriage, through winter. It took months. When they finally arrived in St. Petersburg, the university rejected him. He was from Siberia. A village, really. They didn't want him. So she took him further. She took him to Moscow. Rejected again. Finally, she got into a small teachers' college, a small school. A chance. And weeks later, Maria Mendeleev died. She has spent everything, her health, her money, her life, to give her son a future. Years later, Mendeleev sat alone in his study, surrounded by cards. Each card had an element written on it: sodium, carbon, oxygen, chlorine. He arranged them by weight, how heavy they are, by behavior, over and over and over. And then he saw it, a pattern. Elements on the left gave away electrons. Sodium, potassium, reactive metals, desperate to lose that outer electron. Elements on the right grabbed electrons, oxygen, chlorine, hungry, pulling them in. Elements in the middle shared equally, carbon, hydrogen, builders, forming long, stable chains. But the pattern had holes. If he followed the logic, if he trusted what the table was telling him, there should be elements that didn't exist yet. He could even predict their properties, their weight, how they would behave. And when he published this, the scientific world mocked him.
Gaps? You're just making things up.
But Mendeleev didn't flinch. He had promised his mother. He trusted the pattern. And then, one by one, scientists began discovering new elements. Gallium, scandium, germanium. And they fit exactly where Mendeleev said they would, with exactly the properties he predicted. The gaps were real, the pattern was real. Mendeleev had been right all along. Today, we call it the periodic table. Not just a chart on a classroom wall, but a map of how matter behaves. And now let's use Mendeleev's table to understand soap. Because soap works because of where its atoms sit on that table. Sodium on the left gives up its electron easily. That makes one end of the soap molecule charged. Another word we use is polar, water-loving. Carbon and hydrogen in the middle share their electrons equally. That makes the other end non-polar. We also say oil-loving, lipophilic. One molecule, two personalities. It speaks both languages, water and oil. And grease, grime, bacteria, viruses, they don't stand a chance. Today we're going to make soap from scratch. And when you do, you'll see the pattern Mendeleev discovered. The one his mother died believing in come to life in your hands. So this is the part that I want you to interact. I want you to go get a small bowl of water, and then you're going to put pepper, just black pepper or white pepper. Just sprinkle it on top. And this is going to represent viruses or bacteria. And what you're going to do is touch the surface of the pepper on top of the water and let me know what happens. Now I want you to dip your fingers in some soap or even just rub along a bar of soap if you don't have liquid soap, and then place it on top of the pepper, which is on top of the water. And whoa, did you see what just happened? So what's happening is due to the structure, the amphiphilic nature of the soap. So that's what we're going to get into. So to be able to see how soap works, we need to understand a few concepts. There's the term solubility. Solubility is in general use. So here it's referring to a solid solute and its ability to dissolve in a liquid solvent. Example, a solid solute like salt dissolving in water. The term miscibility is not common. No one in the general population uses it. I've never gone to the market and heard anyone use that term. But in this context, it's referring to how two liquids can merge or mix into each other. So it's referring to a liquid solvent and its ability to dissolve in another liquid solvent. Are we on the same page? So this is like a liquid solvent. You may have ethanol, it's a different liquid to water, and when you bring them together, they can actually mix. But if you bring water and an oil together, they don't mix. So it turns out that these behaviors, these characteristics that we see, are really determined by the atomic structure of three compounds, three molecules. Water, the structure of water, the structure of fats, and the structure of salts, things that we call salts. The other term we need to become familiar with is esterification. What is esterification? To tackle that, what do we know about the structure of fats? So we know that fats actually have a portion that is considered charged, and so this makes it polar or potentially dissolvable in water. But then they have these parts that we call hydrocarbons, and they just don't mix with water. They hate water. And so a fatty acid, a fatty molecule on its own, could have a potential to mix with water somewhat if the polar head was in contact with it. However, fats are stored as these long chains along with another molecule called glycerol. And then we call fats triglycerides. So they don't have the polar charged components anymore, and that's why you see butter or oil will not mix with water because it's been stored in this triglyceride format. So we can perform a reaction called saponification. And if you're familiar with that term, please let me know in the comments. But saponification is basically this idea of replacing the triglyceride, which is insoluble in water, with a molecule that will allow it to be now partly soluble. I'm going to have you predict before mixing which ingredient contributes the water-loving head and which creates the oil-loving tail. And this comes from the idea that, salt. What's the molecular formula for salt? We know it's sodium and it's chlorine or chloride that have come together. And the sodium is charged, positively charged. The chlorine or chloride is a negative ion. And what happens when it goes into water, because of the structure of water, and we're trying to keep this very digestible, because of the structure of water itself is also polar. So water, the arrangement of the atoms, the hydrogen and the oxygen, it's not in a straight line. It's not in a linear way. It's shaped like a triangle. And so one part of it is charged. And so the positive charge of the sodium will interact with a part of the water molecule, and then the chloride ions will also interact with part of the water molecules, and so it essentially strips it apart, and that's what we then see or interpret as or experience as dissolving. So in the chemical reaction of saponification, sodium hydroxide, once again the same sodium, is used to replace the glycerol molecule of triglycerides, so that now we have a component of it that can dissolve in water, the sodium, and the charged part. And then the hydrocarbons are also really not ready to interact with water. And so what happens is we replace the 3 glycerol molecules with 3 sodium hydroxide molecules. And what happens is you get a reaction that results in a fatty acid salt. So salt is basically any molecule that it's so strongly charged that they clump up together and then you can visually see them. So this is what happens in a saponification reaction. The sodium hydroxide replaces the glycerol backbone of triglycerides or oils and fats. And so you end up with this fatty acid salt, so this sodium salt. And so now that is what we know as soap. And what is going on here is that you now have a negatively charged sodium hydroxide or polar head, and then you have a positively charged hydrocarbon tail. And so when they come in contact with grime and grease, the fatty acid can dissolve in the oily liquid, but then the polar head can also interact with water. And so that's how when you then now put water, you're able to clean or rinse away the grease and grime, and any bacteria that's there will be removed, because while the soap will not kill the bacteria directly, it will remove it because it's dissolved in the oils, and so the oily fatty acid components can actually interact with the hydrocarbon bits, and so the water will drag it physically away. It's not left there. And then when you have things like viruses, the soap can actually directly kill it, because these viruses tend to have the envelope, the membrane that is lipophilic, and so the soapy part can actually burst their membranes open and explode and damage them. There are other molecules in our body that are amphiphilic. Let me know if you can think of any, how many you can think of. So we talked about the membrane of viruses. Now, these membranes are actually amphiphilic, because what happens is they have a lipophilic head and a hydrophobic tail, and they tend to arrange themselves in a format where the lipophilic heads will be on the outside and the tails are on the inside, and that's how they form the phospholipids in cell membranes. It's not just soaps. We know that detergents also are amphiphilic molecules where they have a charged component that can dissolve in water, as well as a hydrocarbon chain that will allow it to interact with the fats and dirt and grime in our clothes and be able to remove it. Now, interestingly, your liver makes an amphiphilic molecule, a soap, if you like, and that's what allows you to digest fats that you eat. And then we have surfactants, which are milder things that you will find in shampoos and in conditioners. And these also are amphiphilic. They have charged heads and hydrophobic or non-polar hydrocarbon tails. Now, way back in the 14th century, before Mendeleev brought together the periodic table in Africa, they were making soap, and there are videos of how to make African black soap that you can have a look. They're very simple formulas where they use potassium instead of sodium hydroxide. Potassium from ash is mixed with oil in order to create a fatty acid salt. And when you're making your own soap, you can go to a website to put in the amount of oil you plan to use, the types of oil you're planning to use, as well as what properties you're looking for, and then it will guide you as to how much of each oil to use in order to get the benefits you're looking for.